And first of all, I'd like to thank the organizer for inviting me to this very wonderful workshop. And actually, I'm glad to visit Korea again. So my name is Masatoshi Sato. I'm from Yukawa Institute for Electrical Physics, Kyoto University. And originally, I supposed to give a talk about bulk correspondence in the point gap topological phases. I found that I already gave this talk in another conference in this institute in this June, and I found that my talk was already in the YouTube channel in this institute. So that I determined to change the subject, and today I'd like to explain my recent work on minor fermion in the Perry symmetry in the topological superconductors. And this talk is based on the collaboration with these papers, Shingo Kobayashi and Ai Yamakage and Yuki Yamazaki and Yukio Tanaka. And based on these two papers and the recent progress with Shingo Kobayashi, I will give a talk. And first, I'd like to explain my motivation for these works. And as probably all of you know, topological superconductivity shed a new light on the investigation of the superconductors. Actually, we know that minor fermion can be realized in various superconductors. And probably the most promising candidate having minor zero mode is iron-based superconductors. And actually, this material has a topological insulated nature, so it can support surface Dirac fermions. So in the superconducting state, this surface Dirac fermion can be the topological superconductors. And actually, just so if you create the vortex in the system, so we can expect a minor zero mode in the vortex. And here I show the related STM data, and this is the Chinese data, and this is the Japanese data. And as you can see that both data clearly show the presence of the zero bias peak coming from the probably the minor zero mode in the vortex. And in particular, in the right picture, you can see the zero bias peak well separated from the peak coming from the mini-gap state of the vortex state. So this zero mode, this zero bias peak should be a strong evidence of the presence of the minor zero mode. And we also know that the nodal superconductor also had very nice topological natures. For example, if you consider the high TCQ plate, so we have line nodes, and they have their own topological numbers. So correspondingly, if you create the surface in this direction, so we can obtain the surface flat band because of these topological numbers. And actually, the presence of the surface flat band has been observed by using the tonal conductance measurement. Actually, they measured this kind of zero by B structure even before the discovery of the topological insulators. This is data taken by the Kashpayer-san. And as you can see, this data clearly shows the presence of the zero bias peak. And as you can see that solid line shows the experiment data, and the dotted line shows the theoretical calculation done by the Tanaka-san. And as you can see that these two results shows a very good agreement. So this should be the evidence of the presence of the surface flat band. So in this sense, so that we can say that the high TCQ plate is also the topological superconductors. So we can say that the topological superconductivity sheds a new light on the investigation of the superconductors. And as I mentioned in the previous slide, the most distinctive feature of the topological superconductors is the possible realization of emergent minor fermion in various superconductors. However, in this talk, I'd like to emphasize that we should know that there are two different types of Majorana fermions. Actually, we have a spinless Majorana fermion, and we also have a spinful Majorana fermions. And as I explained below, so actually they have a very different properties. So they probably have a different role in the study of the topological superconductivities. So first, I'd like to explain the spinless Majorana fermions. And the spinless Majorana fermion have only the particle symmetry, namely the charge conjugation symmetry, intrinsic to the superconductors. So they require no particular symmetry, excess of the superconducting gap. Indeed, so that we can show that only the Fermi surface topology in the normal state determine the presence or the absence of a spinless Majorana fermions. Actually, by using the so-called weak pairing assumptions, we can prove the following statement. A spinless Majorana fermion is realized if and only if the corresponding superconductor has an odd number of non-spin Dirichlet Fermi surfaces. For example, here I consider two different Fermi surfaces. In the red pair, so I consider the spin-splitted Fermi surfaces like Rashba systems. In this case, we have two non-spin Dirichlet Fermi surfaces. On the other, in the right case, I consider the single non-spin Dirichlet Fermi surfaces. So according to this simple Fermi surface criterion, we can say that in the left case, so that we don't have any non-spin Dirichlet Majorana fermions. On the other hand, in the right case, we have spinless Majorana fermions. So this is very simple criterion, but by using this criterion, we can explain the presence of the spinless Majorana fermion in various superconductors. For example, we can consider the two-dimensional Dirac fermion coupled with a S-phase condensate. The presence of the Majorana mode in this system was first mentioned in this paper in the context of the high-energy physics. But later, in the context of the condensed matter physics, Liang Fu and Charlie can consider the surface Dirac fermion of the topological insulators and consider the similar Hamiltonians. So anyway, I consider this Hamiltonian, and this is a Dirac Hamiltonian, and this is the S-phase condensate. And as you know, if you consider the Dirac Hamiltonian, we have this kind of single non-spin Dirichlet Fermi surfaces. So this means that once we have create a vortex in the system, we can expect a Majorana zero mode. Actually, this type of spinless Majorana fermion is realized in the iron-based superconductors. Here I show the crystal structure of the iron-based superconductor, and this is iron, and this is selenium or tellurium. And here I show the ALPS data taken by the single at ISSP Japan. And as you can see that this is the normal state spectrum, and this is bulk, this part coming from the bulk, and this part coming from the surface Dirac fermion. So you can see that there exists a surface Dirac fermion in the normal state. And they also measure the gap at the Fermi level in the superconducting state, and this is the data. And as you can see that at low temperature, this surface Dirac fermion shows the superconducting gap. So this means that we can obtain the surface Dirac fermion with the superconducting gap. So from our Fermi surface criterion, we can expect topological superconductivities. And actually, they predict surface topological superconductivity in the system. And as I mentioned before, so this STM data is very consistent with the presence of the Majorana zero mode in the vortex. So in this case, we can confirm the correctness of our Fermi surface criterions. And we also have another example. Here I consider the S-phase superconductor with Rashba superconductor with a Zeeman field. And the presence of the chiral Majorana fermion, in this case, was first established in this paper in the context of the cold atomic systems. And later, they and the collaborator naturally generalize this idea to the semiconductor systems. So anyway, in the absence of the Zeeman field, we have this kind of band structure in the normal state. Now we are considering the Rashba spin-orbit interactions. We have a spin-split band structure like this one. So if you consider the Fermi level here, we have a smaller Fermi surface and larger Fermi surfaces. So we have two non-spin degenerate Fermi surfaces. And correspondingly, here I show the Kesa particle spectrum in the superconducting state with a boundary. And as you can see that, we only have a superconducting gap, like ordinary epsilon superconducting state, and there is no edge state. So this is a non-topological state. On the other hand, if you apply the Zeeman field, we have different situations. Actually, once we have a Zeeman field, we have a gap at the gamma point, so that we can push one of the Fermi surface above the Fermi level. So at the particular value of the Zeeman field, so the topological phase transition occurs. And then if you have larger Fermi surfaces, so that we can realize this situation in the normal states. So in this case, we only have a single non-spin degenerate Fermi surfaces. So correspondingly, in the superconducting side, we have a spinless Mylar fermions. So this behavior is also very consistent with our simple Fermi surface criterions. And originally, we considered a two-dimensional system, but later the Roman Rucci and Yuval Oreg and collaborators generalized this idea to the nanowire system. And we know that in the same parameter region, this nanowire system may support the spinless Mylar fermions. and we have two examples, but we also have one more another example. And actually, interestingly, a similar topological superconductor with a spinless Mylar fermion can be obtained even by using the Rashba-like spin-dependent dispersions. Actually, with Okuma-san, we consider the non-Hermitian Rashba nanowire systems. And instead of the usual Rashba spin orbital interaction, in this paper, we consider the non-Hermitian version of spin orbital interactions. And we also consider the S-pair pairing interactions. And we also add the infinitesimal Zeeman fields. Actually, in the thermodynamic limit, this term can be zero. So anyway, now we are considering this non-Hermitian spin orbital interaction. So we have this kind of pictures. Actually, because of this spin-dependent dispersion terms, we have this kind of pictures. Actually, the forward upspin electron and the backward downspin electron decay due to this dispersion term. So we effectively realize these situations. Forward downspin electron and backward upspin electron only survives. So this means that we can effectively realize a non-spin degenerate single Fermi surface using by the dispersions. So according to our simple Fermi surface criterion, we can expect a spinless Mylar zero mode. And actually, we can obtain a spinless Mylar fermion in this case. Here I show the Kesa particle spectra in the superconducting state. So since now we are considering the non-Hermitian term here, and spectrum can be complex. However, in addition to the bulk spectrum, we also had a zero energy mode, and actually this corresponds to the spinless Mylar fermions. And in this picture, we consider the finite size systems. So the very tiny magnetic field is necessary to realize this picture. This magnetic field can be zero in the thermodynamic limit. So anyway, because of this structure, we can obtain a spinless Mylar fermions. So this means that to obtain a spinless Mylar fermions, only the information of the Fermi surface is necessary, and no particular Schmeller symmetry is required. That is the reason why we can realize a Mylar fermion even for the S-pair pairing interactions. So now I'd like to consider the second type of Majorana fermions, namely the spin-full Majorana fermions. So as you know, the most superconductors have spin degenerate Fermi substitutes. So this means that they can only support spin-full Majorana fermions. And interestingly, in contrast to the spinless Majorana fermions, symmetry plays a very crucial role in the realization of the spin-full Majorana fermions. And for example, let's consider the mirror reflection symmetries. And here I show the particular material, 1 platinum 3. And this is a crystal structure of the 1 platinum 3. And as you can see that this crystal structure supports the mirror reflection symmetry with respect to the z directions. So if you consider the BGG Hamiltonian, BGG Hamiltonian is invariant under the mirror reflection symmetries. And now consider the mirror invariant plane in the momentum space. If you consider the mirror invariant plane in the momentum space, this equation implies that the BGG Hamiltonian commute with the mirror operators. So this is very simple equation, but this simple equation gives important information for the topological property of the systems. And actually, like ordinary topological crystal insulators, KZ equals 0 plane can be separated into 2 mirror subsectors. So now we are considering the spin-full system. We have upspin electron and downspin electrons. But if you use this relation, we can block diagonal the Hamiltonian by using the eigenvalue of the mirror operators. And in this particular case, mirror operator is proportional to the spin in the z directions. So if you consider the mirror plus subsectors, we only have upspin electrons. And if you consider the mirror minus subsectors, we only have downspin electrons. So we can effectively realize a spinless system. So we can introduce the so-called mirror channel number. And if the mirror channel number is non-zero, so from the bulk bundle correspondence, we can say that we have a gapless surface state. However, we should notice that the obtained surface state not necessarily the Majorana fermions. And actually, we have additional requirement to realize the Majorana fermions. Actually, we need particle symmetry to obtain Majorana fermions. Actually, so particle symmetry gives the Majorana condition for the wave function of the K-side particles. So this symmetry is very important to realize Majorana fermions. So in the superconducting state, we actually have, in addition to the upspin electron and the downspin electrons, we also have upspin hole and the downspin hole. And they are related by the particle symmetries. So the problem is how the particle symmetry is realized in the mirror subsectors. And actually, we have 2 different realizations of the particle symmetry depending on the pairing symmetries. For example, let's consider mirror-even pairing symmetries. In this case, gap function is invariant under mirror reflection symmetry. So the mirror reflection symmetry is trivially realized in the superconducting state. So in this case, we found that the particle symmetry is realized in this manner. Actually, so if you perform the particle symmetry to the upspin electrons, we have upspin hole in the different mirror subsectors. And we also found that if you apply the particle symmetry to the downspin electron, we also have a downspin hole in the different mirror subsectors. So the other hole systems, we have a particle system, but each mirror subsector doesn't have a particle symmetry. So this means that each mirror subsectors realize a quantum hole state like ordinary topological crystalline insulators. So this means that like ordinary topological insulators, we just obtain the Dirac fermion in the systems. But the situation can be different if you consider the mirror or the pairing symmetries. In this case, we have additional minus sign in the transformation law for the gap functions. And the particle symmetry is realized in this manner. Actually, we can show that if you apply the particle symmetry to the upspin electrons, we have an upspin hole in the same mirror subsectors. And the same situation can happen even in the mirror minus subsectors. So this means that as well as the whole system, we have a particle symmetry for each mirror subsectors. So this means that each mirror subsectors can realize the topological superconductors, so we can obtain the Majorana fermions. So this means that we have a Majorana fermion only for the mirror auto superconductors. So this argument tells us that the symmetry and the pair symmetry are important to realize the spin-full Majorana fermions. So the spin-full Majorana fermion can have some information about the pairing symmetries. For example, let's consider the one-parameter 3. As I mentioned before, the one-parameter 3 has a mirror reflection symmetry with respect to the z directions. Here I show the theoretically proposed phase diagram for the one-parameter 3. And, this is the temperature, and this is the magnetic field in the z directions. So here we should note that the magnetic field in the z direction does not break the mirror symmetries. So we can apply the argument in the previous slide to this phase diagram. So now I consider this particular phase B. And according to the Zell theory, so the phase B realizes mirror auto superconductance. So we have additional minus sign here. So according to the argument in the previous slide, so that we can expect a spin-full Majorana fermions. And actually, we can confirm this expectation by creating a vortex in the z directions. This configuration also does not break the mirror reflection symmetries. And here I show the spectrum calculated by the Tsutsumi-san. And here I consider this particular mirror invariant momentum. And this is spectrum. This comes from the Bar spectrum. And in addition to this one, we also have a mini gap state inside the vortex. And as you can see, we have a zero energy mode. And this is actually the spin-full Majorana zero mode. So in this case, we can nicely obtain the spin-full Majorana zero mode. And here I showed another example, and namely the recently discovered superconductor, cerium rhodium-2 arsenic-2. And this is a crystal structure of the cerium rhodium-2 arsenic-2. And unfortunately, this crystal structure does not support mirror reflection symmetry. But instead of a mirror reflection symmetry, this crystal structure supports grid reflection symmetries, a kind of mirror reflection symmetries. So by using the similar argument, so that we can conclude that if you can realize a grid or the superconducting state, so that we can expect a spin-full Majorana fermions. And here I show the experimentally obtained phase diagram of the system. This is temperature, and this is magnetic field in the z directions. And this magnetic field does not break the grid reflection symmetries. And according to the theory by the Yoshida-san and Shigeru-san and Yanase-san, and they found that they predict the two superconducting phases, low field superconducting phases and high field superconducting phase. And they predict that in the low field phase, realize even parity superconducting state, and high field phase realize odd parity superconducting phase. But in more detail, and they also predict that in low field phase is grid even superconducting state, and the high field phase is grid odd superconducting phase. So they predict these two phases. And so according to argument in the previous slide, so that we can conclude that if you can obtain this second phase, so that we can expect the Mylar fermions. Actually, the Yanase and the collaborators show that actually in this phase there exists the Majorana fermions. And here I show the one more another examples. And very recently, the similar idea also has revealed positive Mylar fermion for S plus minus wave pairing state in iron-based superconductors. Here I show again the crystal structure of the iron-based superconductor. And from top view, so that we have this kind of crystal structures. Crystal symmetry is P4NMN. So that this means that we have inversion symmetry and two different mirror reflection symmetries. And importantly, in this case, they have different centers. So that this means that so the symmetry is non-symmorphic. So anyway, so in this talk, I focus on the mirror reflection symmetry. So we have these two different mirror reflection symmetry. And here I focus on the mirror reflection symmetry with respect to the y directions. And here I show the spectrum along this mirror invariant moment. So as you can see that this is Fermi level. So around the M point, we have two Fermi surfaces, smaller one and larger one. So now we are considering the S plus minus wave superconducting state. Gap function have opposite sign between the smaller and the larger Fermi surfaces. And usually, so that we don't expect any topological superconductivity in S plus minus wave superconductors because they belong to the same representation as the ordinary S wave superconducting state. But by using the crystal symmetry, we can obtain different conclusions. Actually, now the BD Hamiltonian commute with the mirror operator. So we can break down the Hamiltonian by using mirror operators. And we have this kind of spectrum in the normal state. So actually in the mirror plus sector, we have this one. And the mirror minus sector, we have this one. And importantly, so once we have a mirror subsectors, we have opposite sign in the gap function in the opposite side of the Fermi surfaces. So this means that we can effectively realize the P-wave superconducting state. So this means that we can obtain topological superconductivities. And actually, if you create the surface preserving the mirror symmetries, so that we can obtain the corresponding surface state. However, more importantly, if you consider the particular edge, then we can obtain the Majorana zero mode. Here I show again the crystal structure of this material, and here now I consider the 1,1 edge and 1,1 bar edges. So as I mentioned before, this crystal structure has a mirror reflection symmetry with respect to this axis. And as you can see, that these two edges are interchanged by the mirror reflection symmetries. So this means that we don't expect any surface state produced by the mirror reflection symmetry for these two edges. However, as you can see that if you consider this corner is invariant under the mirror reflection symmetry. So we can obtain mode protected by the mirror reflection symmetries. And actually, we can obtain the Kramer's pair of the Majorana corner mode because we have a time reversal symmetry in the systems. And here I show the numerical calculation done by them. And actually, they show that there exists 8 zero mode in this configuration. So which means that there exists Kramer's pair of Majorana zero mode for each corners. So anyway, the crystal symmetry enables the topological superconductor have a spin-full Majorana fermion even in time reversal invariant S plus minus wave superconductors. So now I'd like to ask the following questions. So as you know, the spinless Majorana fermion can be topological qubit as a non-abelian ions. So the natural question that do spin-full Majorana fermion have a useful application in the condensed matter physics? And some people say that even for the even spinful Myra fermion can be used as a topological qubit, but usually we need symmetry protection in the braiding process, and I think it is not so easy. So I try to search another role of the spinful Myra fermions. And actually the answer is yes. And actually we found that they exhibit very unique electromagnetic responses, and which may directly determine the pair symmetry of various unconventional superconductors. So as you know, the determination of the pair symmetry of the unconventional superconductor is very difficult. But our theory suggests that the spinful Myra fermion can have useful information about the pair symmetry, and by using this information, so that we can somehow determine the pair symmetry of the various unconventional superconductors. So in the remaining time, I'd like to explain the main topics of this talk, and based on these two papers. And before going to the detail of our theory, so first I'd like to explain how the pair symmetry is encoded in the topological classifications. And actually in the topological classification, all the information of the symmetries are compactly encoded in the following three relations. In the first relation, specifies the type of the symmetries. Here UG is a symmetry operator, and H is a Hamiltonian. And we found that if the CG equals +1, in this case, this relation gives ordinary symmetries. However, if the CG equals -1, we have additional minus sign here. So this means that symmetry is anti-symmetry, like a chiral symmetry or the particle symmetries. And the second equation specifies the neutrality or the anti-neutrality of the symmetries. And here I is imaginary unit in the complex number. And if the phi is equal +1, in this case, symmetry operator commutes with the imaginary unit I. So this means that the symmetry operator is a neutral operator. On the other hand, if the phi is equal to -1, in this case, we have additional sign here. So this means that the symmetry operator anti-commute with the imaginary unit I. So this operator should be anti-neutral. And the last equation specifies the commutation relation between the symmetry operators. And this part is called as a twist. And we know that most systems have a trivial twist just determined by the point group relations. But some may have a non-trivial one. Actually, we discovered that if you consider the unconventional superconductor, we may have a non-trivial twist. Or if you consider the non-symmorphic crystals, we also have a non-trivial twist. So anyway, in this talk, I focus on this unconventional superconductivities. And actually, the information of the pair symmetry is encoded in the twist between the particle symmetry and the crystal symmetries. For example, let's consider the odd party superconducting state. Here, P is the operator for the inversion symmetry. And if you consider the odd party superconductors, we have additional minus sign here. And this means that if you consider the number space, inversion operator should be defined in this manner. Because we have a minus sign here, so to have inversion symmetry for the BG Hamiltonian, we need a minus sign here. And this part acts on the particle, and this part acts on the whole, and we have additional sign here. So this means that the particle and the whole behave in a different manner under inversions. So this means that the particle symmetry is not compatible with inversion symmetries. So this means that we have additional minus sign in the computation relations. So anyway, for the general symmetries, we have this kind of relations. If you have additional factor here, So that we also have additional factor in the computation relation between the particle symmetry and the symmetry operators. So in this manner, so that we have information on the pair symmetry in the computational relation between the symmetry operators. So now I'd like to explain the response of the Majorana fermions. And actually, to evaluate the possible response of Majorana fermion, we consider the very general local operator of electrons. Here, C denotes the creation or the annihilation operator of electron, and sigma denotes the internal degree of freedom, like a spin or the orbitals. And O is the Hermitian operators. And so by using the so-called number spinor, so that we can relate this relation to this one. Here, the curly O is defined by these relations. So anyway, so we consider this local operators. And first to extract the contribution of the Majorana fermion, we first perform use the particle symmetry of the number spinors. Because the number spinor has this particular form, we can show that if you apply the tau x from the right, so that we can change the Hermitian conjugate to the transport θ. So we have this kind of relations. And then we perform the model expansion of the quantum field. So that we can have a contribution coming from the gapless Majorana fermion here. And then if you substitute this into the original operator here, so we can identify the contribution coming from the Majorana fermions. And here, law operator is defined in this manner, and CU star A is defined the particle symmetry partner of Majorana fermions. So in here we have this kind of operator, and so this means that if this trace part becomes non-zero, then we have a non-trivial coupling between the Majorana fermions. So this means that law operator determines the possible local operators of Majorana fermions. So this operator is very important to determine the possible response of the Majorana fermions. And interestingly, this law operator transforms like as a byproduct of the electron, like a Cooper pair under the crystal symmetries. Here I show again the definition of the law operators. And now consider the transformation law of under the crystal symmetries. And actually, we know that if you have a crystal symmetry, Majorana fermion move to another Majorana fermion by the crystal symmetries. So this means that if you apply the crystal operator to the Majorana fermion, then we have a linear combination of the Majorana fermions. So this means that this Majorana fermion behave like a projective revelation of the crystal symmetry, like electrons. And we also have a transformation law of the particle symmetry partner in the similar manner. And actually, in this case, we can use the computation relation between crystal operator and the particle symmetry operator, so that we have additional sign here. And finally, in this part, we can use these relations. And then finally, if you use the anti-utility of the particle symmetry, we have a complex conjugation here. So this means that the particle symmetry partner behave like a projective representation like a whole. So and finally, so by using these two relations, we can obtain the transformation law for the law operators. So if you calculate these relations, then we have this one. So now we have a complex conjugation here. So the complex conjugation come back to the original one. So that we have these relations. And so this means that the law transform like as a byproduct of electron like a Cooper pairs. And we also have this non-trivial factor here. And so this comes from the pair symmetries. So this means that Majorana fermions know the pair symmetry of the Cooper pairs. And in particular, we have a direct relation between Mylar fermion and the pair symmetry if you consider single Mylar column mass pair produced by the G. In this case, they are related by the time reversal symmetries. So the rho consists of the column mass pair. So this means that if this part has upspin electrons, and this part behave like downspin electrons. So and now we have an anti-symmetric combination. So this means that this part behave like a spin singlet. And we also know that if you consider a single Mylar fermion produced by the symmetry G, then G preserves the position of the Mylar fermions. So this part only contains the spin contribution. So as I mentioned before, the rho behave like a spin singlet. So this means that this part should be trivial. So that we have this relation, and this is almost the same as this relation. So this is the same representation as the gap functions. And we also found that under the time reversal symmetry, we also have these relations, and actually we have additional minus sign here. So this means that the rho operator is actually the magnetic operator. So we can conclude that the single Mylar column mass pair produced by the G has a magnetic structure with the same representation as the gap functions. So by using this information, we can determine the magnetic response of the spin-full Mylar fermions. So finally, I'd like to apply this argument to the various superconductors. Actually, we have a complex classification in this paper, but in this talk, I explained two particular examples. First one is the high spin topological superconductors. And in this case, I consider the yttrium platinum bismuth. And this is a well-known high spin superconducting state. And the experimental results show the superconducting at low temperature, and it also shows the presence of the line node. And to explain these nodal structures, they propose parity mixed superconducting states. Actually, so this material doesn't have no inversion symmetry. So this is non-central symmetric superconductor. So it allows to have a parity mixed superconducting state. Importantly, because of the higher spin structures, so the superconducting gap has a multiple structure due to higher spin. So the correspondingly, so that we can expect this kind of higher spin response, magnetic response, of the spin-full Mylar fermions. Actually, we found that if you consider the one-for-one surface, we can obtain octopole responses. So this is very consistent with our theoretical argument. And here I showed another example, S plus minus wave topological superconductors. As I mentioned before, so this system supports the Mylar corner mode protected by the mirror reflection symmetries. So this means that the magnetic structure of Mylar fermion should be trivial under the mirror reflection symmetry, since we are considering the trivial representation under the mirror reflection symmetries. And so this means that so we also know that this should be the magnetic structure. So that this should be the odd under the time reversal symmetries. So this means that the consistent magnetic spin structure should be the eigenspin in these directions. So if you can detect this kind of structure by using the STM measurement, so that we can directly have the evidence of the Mylar fermion protected by the mirror reflection symmetries. So anyway, so the observation of the magnetic structure via STM can establish this exotic pairing state. So let me summarize my talk. We discussed the relation between the pair symmetry and the spin-full Mylar fermions. And we developed a systematic way to evaluate the quantum response of spin-full Mylar fermion, show that magnetic response of spin-full Mylar fermion can identify the pair symmetry of the Cooper pairs. And actually, the detection of the magnetic response of spin-full Mylar fermion gives a direct evidence of the executive topological superconductor, such as higher spin topological superconductivity or S plus minus wave topological superconductivities. Thank you very much for your attention.
Thank you very much, Masatoshi Sato, for this very nice talk. Questions? Yes, please. There is a question.
Thank you very much for the nice presentation. I have one quick question about the some G-man field effect to the S plus minus the spot conducting structure. Where it breaks the time reversal symmetry, but I guess some pairing spot conducting pairings remains the same. Then can I have some comments about what you would expect? How this change the Majorana-Fermion spinful Majorana-Fermions?
So actually, so this means that this implies that this Majorana-Fermion can feel the spin, can feel the magnetic field in this direction, and so in the original theory, we have time reversal symmetry, and in the absence of time reversal symmetry, you may consider that we don't expect any zero mode, but this is not correct, and actually to have a splitting in the zero-net state, we need a magnetic field in this direction. So if you apply this magnetic field in this direction, so in this case, we don't have any splitting of the Majorana zero mode. So even without the time reversal symmetry, we can keep the spinful Majorana-Fermion. And this is the conclusion of our general theory. And this kind of unisolated behavior is very consistent with the symmetry protection of the spinful Majorana-Fermions.
Thank you. Thank you very much.
There's another question in the front.
So you formulated this Fermi surface criterion for spinless Majorana-Fermions. I was wondering, how do you define a Fermi surface in a non-Hermitian setting?
Fermi surface. Actually, the Fermi surface is defined in the normal state, and we assume the wave pairing assumption. So this means that we can we assume that the gap function can be small without the gap closing, and in a usual superconductor, and this assumption is always works because the gap function is very tiny, and that is my assumption. So the Fermi surface is defined in the normal state.
I understand, but when you're in a normal state and you have a non-Hermitian
in the non-Hermitian case?
Yes.
In non-Hermitian case, it's not so easy. But we can say that we have a different lifetime in between this configuration and this configuration. And we found that this configuration is a longer lifetime. So in this sense, we can satisfy the Fermi surface criterion.
But how do you define the Fermi surface generally in a non-Hermitian setting?
Defined in the real part of the energy becomes zero. So by using the real part of the Kesa particle spectra in the normal state. And Okay. So in this case, I assume that in the normal state, there is no gap in the real part spectrum, and that is the definition of the Fermi surface.
I mean, I have two more questions.
Okay, one, and the second one for the lunch break then, please.
So you mentioned that this iron-based superconductor has a single surface direct fermion.
Yeah.
So does it mean that it's a topological insulator in the normal state?
No. So in addition to this contribution, we also have. So I don't have a. So actually, in this particular direction, so we only have this surface state, but in other directions we have a bulk contribution, and this bulk contribution becomes the superconductor. So in the normal state, the system is basically the metal, but in addition to the metallic part, so we also have a surface contribution.
Isn't it strange to have a single surface direct fermion on any surface? There must be something topologically non-trivial in the bulk, right?
So in the momentum space, they are well separated. In the momentum space, they are well separated from each other. So in some part of the momentum space, we have a surface state. In the other part, we have a bulk spectrum.
Okay, I understand. Thanks.
Okay, are there other questions from the audience? Maybe I can just ask one little, what's the glide reflection symmetry?
Pardon?
What is a glide reflection symmetry? I think on page 14.
So the glide reflection symmetry is just a combination of the symmetry plus half translations.
Can you repeat again, please?
In this system, so if you consider the mirror reflection symmetry, so that we don't have exact same crystal structures, but if you perform the half translation in under the along the mirror plane, then we have a same crystal structures.
Thank you. Okay, I think we should maybe now move on to our lunch break, and let's thank both our speakers of the morning session. Thank you very much.